In this video, we will discuss complements, conditional probability, and Bayes' theorem. The probability of at least one. When finding the probability of some event occurring at least once, we should understand the following. At least one has the same meaning as one or more. And the complement of getting at least one particular event is that you get no occurrences of that event. For example, not getting at least one girl in 10 births is the same as getting no girls, which is also the same as getting 10 boys. Finding the probability of getting at least one event of some particular event. Let A equal getting at least one of some event, then the complement of A is getting none of that event. Find the probability of the complement of A, the probability that event A does not occur. Then subtract the result from 1, that is, evaluate. The probability of at least one occurrence of event A is equal to 1 minus the probability of no occurrences of event A. For example, a study by SquareTrade found that 6% of damaged iPads were damaged by bags or backpacks. If 10 damaged iPads are randomly selected, find the probability of getting at least one that was damaged in a bag or backpack. Is the probability high enough so that we can be reasonably sure of getting at least one iPad damaged in a bag or backpack? Let A equal at least one of the 20 damaged iPads was damaged in a bag or backpack. Identify the event that is the complement of A. The complement of A is not getting at least one iPad damaged in a bag or backpack among 20. So all 20 iPads are damaged in a way other than a bag or backpack. Find the probability of the complement by evaluating the probability of the complement of A. The probability of the complement of A is the probability that all 20 iPads were damaged in a way other than a bag or backpack, which is 0.94 times 0.94 times so on and so forth times 0.94. That's 20 0.94s being multiplied together. So that's 0.94 to the 20th power, which is 0.290. Now we find the probability of A by evaluating 1 minus the probability of the complement of A, which is 1 minus 0.290, which is 0.710. For a group of 20 damaged iPads, there is a 0.710 probability of getting at least one iPad damaged in a bag or backpack. This probability is not very high, so to be reasonably sure of getting at least one iPad damaged in a bag or backpack, more than 20 damaged iPads should be used. Conditional probability. A conditional probability of an event is the probability obtained with the additional information that some other event has already occurred. The probability of B given A denotes the conditional probability of event B occurring given that event A has already occurred. We've got two approaches here, as we have for most things in probability. The intuitive approach, the conditional probability of B occurring given that A has occurred, can be found by assuming that event A has occurred and then calculating the probability that event B will occur. The formal approach, the probability of B given A can be found by dividing the probability of events A and B both occurring by the probability of event A. So that's the probability of B given A is equal to the probability of A and B divided by the probability of A. Recall the results from 555 drug tests of job applicants where 45 applicants both tested positive and used drugs, 5 tested negative and used drugs, 25 tested positive and did not use drugs, and 480 tested negative and did not use drugs. If one of the 555 test subjects is randomly selected, find the probability that the subject had a positive test result given that the subject actually uses drugs. Let A be the event that the subject uses drugs and B be the event that the subject had a positive test result. Then the probability of A equals 50 over 555, which is 14 over 111. and the probability of A and B is 45 over 555, or 9 over 111. We don't really have to simplify that. And that should have been 10 over 111 for the probability of A. Sorry about that. Then the probability of B given A equals 45 over 555 divided by 50 over 555, which is 45 over 50, or 0.900. 90%, if we're going to read it as a percent, which we shouldn't. If one of the 555 test subjects is randomly selected, find the probability that the subject actually uses drugs, given that he or she had a positive test result. Let A be the event that the subject had a positive test result, and B be the event that the subject uses drugs. The probability of A is 70 over 555, and the probability of A and B is 45 over 555. Then the probability of B given A is 45 over 555 divided by 70 over 555, which is 45 over 70, or 0.643. Note that in our example, the probability that the subject has a positive test given the subject uses drugs is not the same as the probability that the subject uses drugs given that the subject has a positive test. In general, the probability of B given A is not equal to the probability of A given B. To assume that they are equal or to use one value in place of the other is called confusion of the inverse. Consider the events D, it is dark outdoors, and M, it is midnight. Ignoring geographic areas above the Arctic Circle and below the Antarctic Circle where the sun may not set at certain times of the year, consider the probability of D given M equals 1. It's certain to be dark given that it is midnight. And the probability of M given D is approximately 0. Since the probability that it is exactly midnight, given that it's dark. Here, the probability of D given M is not equal to the probability of M given D. Confusion of the inverse occurs when we incorrectly switch those probability values or think that they're equal. And to clarify, the probability of M given D is about 0 because it's dark all night, and the chances that it is exactly midnight when it is dark are pretty small. They're infinitesimally small. Bayes' theorem gives the probability of an event based on new information that is or may be related to the event. Using the formula, the probability of A given B is equal to the probability of A times the probability of B given A, divided by the probability of A times the probability of B given A, plus the probability of the complement of A times the probability of B given the complement of A. Suppose that 1% of the population has cancer. Denoting the event of having cancer by C, we have the probability of C is 0.01 for a subject randomly selected from the population. We also know, regarding a particular test for cancer, that the false positive rate is 10%, while the true positive rate is 80%. So the probability that a positive test result giving cancer is not present is 0.10, and the probability that a positive test result giving the cancer is present is 0.80. Find the probability of C given positive test results. That is, find the probability that a subject actually has cancer given that he or she has a positive test result. We will calculate this probability in two ways. First, we will construct a hypothetical population with the above characteristics, and then we will use the formula associated with Bayes' theorem. Assume we have 1,000 subjects. By our supposition, 1% of the population has cancer. That is, 10 people. The other 990 subjects do not have cancer. Among the 990 subjects without cancer, 10%, or 99 people, get positive test results. The remaining 891 have negative test results. Among the 10 subjects with cancer, 80% of the test results, or 8 results, are positive. The other 2 results are false negatives. To calculate the probability of C given positive test results, we note that there are 107 people with positive test results, but only 8 of them have cancer. So the probability of C given positive test results is equal to 8 over 107, or 0.0748, about 748 10,000ths. Now, using Bayes' theorem, we know that the probability of cancer is 0.01. The probability of a positive test result given cancer is 0.80. The probability of no cancer is 0.99, and the probability of a positive test result given no cancer is 0.10. By Bayes' theorem, the probability of C given a positive test result is the probability of C times the probability of a positive test result given C divided by the probability of C times the probability of a positive test result given C plus the probability of not C times the probability of a positive test result given not C, which is 0.01 times 0.80 divided by 0.01 times 0.80 plus 0.99 times 0.10, which is again 0.0748. Bayes' theorem is important and useful because it can be used with sequential events, whereby new additional information is obtained for a subsequent event, and that new information is used to revise the probability of the initial event. In this context, the terms prior probability and posterior probability are commonly used. A prior probability is an initial probability value obtained before any additional information is obtained. A posterior probability is a probability value that has been revised by using additional information that is later obtained.